Hello, my presentation is about assessing the potential of multi-frequency spaceborne SAR data for the retrieval of snow-water equivalent. The snow-water equivalent, SWE, describes the amount of liquid water in a snowpack and can be approximated by the product of snow depth change and density set in relation to the density of water. SWE is an important parameter for hydrological and climate models, and it is essential for water resource management and planning. Furthermore, SWE is also very important for flood prediction. And as the microwave signals penetrate into dry snow, SAR measurements are sensitive to the structural properties of snow like depth and density. The test site where the in situ measurements were made is located near the city of Zurich in the north of Finland. Snow and air properties, like for example SWE, temperature and depth, are measured here. For repeat pass SAR interferometry, a SWE retrieval model can be used, which relies on the fact that radar waves are refracted in the snow. The SWE change can be calculated with following formula. Alpha is a parameter around 1, which can be adjusted for different densities and incidence angles. K is the wave number, and theta is the incidence angle. In the left plot, you can see the SWE change independence of the phase for an incidence angle of 30 degrees for X, C, and L band. A linear dependence can be observed, and that the SWE changes are larger for L band compared to X band. However, it has to be taken into account that the differential phase lies in an interval between -pi and pi. Therefore, for values outside this interval, phase wrapping errors would be obtained. In the right plot, you can see the absolute value of the maximum SWE change before a phase wrapping error, independence of the incidence angles for the three frequencies. Here again, the values for longer wavelengths are higher. In the next step, the SWE will be estimated for X, C, and L band. Here are the results from the Tandem X data for the winter 2010-11 with a temporal baseline of 11 days. The results from the retrieved SWE values are displayed in blue, and in red you can see the ground measurements. The first point was offset corrected, but still an increasing discrepancy between both measurements can be observed. This results from the fact that the measured SWE changes are sometimes up to 21 mm, while the retrieved SWE changes of this Tandem X measurements can just be up to 8.4 mm due to the phase wrapping. Here it is shown with the phase. In red you can see the phase, which would be obtained from the ground measurements by using the equation on the top right. In pink you can see the Tandem X phase, which can only lie in a range between -pi and pi. Therefore, regions outside this interval cannot be retrieved due to the phase wrapping errors. However, when ground-based measurements are available, these errors can be corrected by adding a phase cycle of 2π when the measured phase lies outside the green interval and the difference is larger than pi. By doing this, following results are obtained with a high agreement between the measured and the retrieved SWE values. To investigate C-band data, Sentinel-1 data over Finland with a temporal baseline of 6 days from the winter 2019-20 was chosen. In the graph you can see the corrected SWE difference in blue for Sentinel-1 and in green for the ground measurements over the winter. It can be observed that for some points the agreement is very high, nevertheless for some other points the difference is very large. By looking here more detailed into the ground measurements, for the first point it can be observed that the temperatures are around or above 0 degrees. Therefore, some melting might have taken place. For the second point, the temperature drops rapidly shortly before the second acquisition. This might be the reason for the deviation, but have to be analyzed more in detail. The ALICE-2 satellite was chosen for L-band data for the same winter over Finland with a temporal baseline of 14 days. Here you can see again the SWE difference for the in situ and the satellite measurements. For the SWE changes in this winter, phase wrapping did not occur for L-band, but it can be seen that for some points the difference between the measurements is very high, like for example in this case. This time frame corresponds roughly to the one from the last two measurements of the Sentinel-1 data. It can be seen that in the beginning the temperature is relatively stable, but then fluctuates a lot and rises up to 0 degrees. Since the temporal baseline of the Sentinel-1 satellite is just 6 days, this time frame can be divided into two parts. With the splitting into two shorter periods, the changes are not so large and the retrieval works better. Therefore, a temporal baseline of 14 days seems to be too large. However, L-band measurements can be affected by the ionosphere, which have not been considered yet. To sum it up, in this case the SWE change before phase wrapping was for X-band ±8 mm and for C-band ±13 mm. For larger values, phase wrapping occurs, but when ground measurements are available, the phase wrapping can be corrected with the result of a good performance. For L-band, this value is higher, but the revisit time of 14 days is long. However, ionospheric effects have not been considered yet. This will be one of the next steps. Furthermore, the plan is to explore dual copolarized data, since the copolar phase difference contains information on the depth and can help to detect when phase wrapping occurs without the need of in situ measurements. Thank you for your attention.